All right, welcome everybody. So we've defined what a quadratic form is in Rn. So what I want to do now is take a look at a couple of examples of functions and let's determine whether or not these functions are quadratic forms. And if they are, then let's find the matrix of the quadratic form. So let's start with number one. So question number one has the following function: q of x is equal to 3x1 minus x1 times x2 plus 8x2 squared. And so we would like to express this quadratic form in the form of x transpose ax. So here we're dealing with R2. So we have x is x1, x2. We have a 2 by 2 matrix, which again needs to be symmetric. And then we have our column vector x. So taking the product and multiplying this out, we're going to get a11 x1 squared plus a22 x2 squared plus a12 plus a21 times x1 x2. So we can see that a11, that's going to be the term 3 in front of x1 squared. a22, that's going to be the 8 in front of the x2 squared. And then for this term that has the product of x1, x2, calling this like a mixed term. This is often called a cross product term. This involves the two off-diagonal entries, a12 and a21. And so recall that these off-diagonal entries this is a symmetric matrix, so they must be equal to each other. So a12 plus a21, that's the same thing as 2 times a12, which is the same thing as 2 times a21. Okay, so now we are ready to summarize our results here, and we found that a11, that came from the coefficient in front of the x1 squared term, and that was 3. The other diagonal entry, a22, that comes from the term in front of the coefficient in front of the x2 squared term, and that was an 8. And then for the off-diagonal entries, we have this condition relating to the mixed term here. So we know that 2a12, that needs to equal the minus 1 that we have as the coefficient in front of the x1, x2 term. So dividing by 2 gives us, excuse me, that a12 is going to equal minus 1/2, and that should also equal a21. So what we get is a 2 by 2 matrix A, where the diagonal entries, the first diagonal entry is 3 and the second is 8. And then the off-diagonal entries, which are equal to each other, in this case is minus 0.5 in both positions. So here we've got our matrix for the quadratic form in question 1. And again, it's worth emphasizing that we get the diagonal entries from the x1 squared, x2 squared terms, and we get the off-diagonal entries relating to these cross product terms that have the combined x1, x2 products in them. All right, let's take a look at the next question, which gives us a function q of x, where x is a vector in R2 in this example, is equal to 5x1 squared plus 3x2. And here we have a quadratic term for x1. Notice the term over here, 3x2, the x2 occurs to the first power. So when we have a quadratic form, we cannot have any linear terms. So no linear terms can exist, but we have one in this expression, namely the 3x2, so this is not a quadratic form. So not every function is a quadratic form. They need to have a very special form, namely that they can be written in the form of x transpose times symmetric matrix A times x. Okay, so let's take a look at number 3. So in question 3, we have that q of x is equal to 5x1 squared minus 3x2 squared, and we don't have any cross product, any mixed terms over here. So for this one, let's just build off of this idea that we had from question 1, which says that the term in front of the x1 squared, that's the first diagonal entry. So this 5 must go right here in this first diagonal position. The coefficient in front of the x2 squared, that gave us the other diagonal entry. So in this case, that's going to be a negative 3. And now we don't have any cross product term that has an x1 times an x2 in it. So this means the off diagonal entries are both 0 here. So we see this nice property that when our quadratic form does not have any of those cross product terms like x1 times x2, that the matrix of the quadratic form actually is going to wind up being a diagonal matrix where the diagonal entries are just exactly the coefficients in front of each of the squared terms. Okay, so one more to take a look at. In question 4, we now have a quadratic form whose equation is 2x1 squared plus 8x2 squared plus 9x3 squared minus 2x1 x2 plus 10x1 x3. So here, the x1, x2, x3s, they all come to the second power. They're all squared. And then we have these interaction terms over here. So this seems like we should be able to find a matrix, symmetric matrix A, to express this function as this product x transpose times symmetric matrix A times x. So let's pull off the information that we can get pretty readily, which is the diagonal entry. So I know that this entry in front of the x1 squared, that 2 is going to be my first diagonal entry. This 8 in front of the x2 squared, that's my next diagonal entry. And then finally, this 9 in front of the x3 squared term, that is my third entry. And we want to pay attention to the signs, but these are all positive. So we have positive diagonal entries. That's not necessarily going to be the case. We can have negative coefficients, and then our diagonal entries might be negative. Okay, so now let's consider the mixed terms, and they are going to tell us something about the off-diagonal entries. So from the first term here, we see that in front of x1, x2, I get minus 2 should equal 2 times a12. From the mixed term with x1 and x3, well, here we see that 10 is going to equal 2 times entry a13. And notice that this formula for the quadratic form above, it could have an x2, x3 term in it, but it does not. So that term is missing. So we do need to account for the a23 entry. And we know that 2 times a23 is going to equal 0 since we don't have any term with x2, x3 in it. And so now we're ready to solve for the entries off of the main diagonal. And so for example, the entry a12, that's going to be minus 1. The entry for a13, therefore, is going to be 5. And the a23 entry is 0. So we can fill in these off-diagonal entries. You got a minus 1 in a12, a 5 in a13, 0 in a23. And then we take their corresponding images over the diagonal entry and set up this symmetric matrix A. So here's our matrix for this quadratic form. It has first column 2, minus 1, 5. Second column, minus 1, 8, 0. And then the third column is 5, 0, 9. Okay, and so let's just summarize a couple of the main points before we wrap this up. And that is the diagonal entries in all of these examples we found by looking at the coefficients in front of the xi squared terms. So from those terms, we get the diagonal entries. And the off-diagonal entries, those come from the mixed terms in the formula, here and over here. So to find aij, assuming that I is not equal to j, we take the coefficient in front of the mixed term, we divide it by 2. And so that's going to be the value for aij, and for j, aji. So it's going to be the mixed terms in the formula, if there are any, that are going to tell us the values for the off-diagonal entries. And it's the coefficients in front of the squared terms that are going to tell us the entries on the main diagonal.